in sections 9 through 11 of Chapter 2, we're going to put together all of this quantum mechanical treatment and understand how that affects electron structure. So in sections 9 and comma 11, because some of this is a little bit out of order due to the nature of explanation, we're going to talk about how polyelectronic atoms change the degeneracy of orbitals. We'll explain the Aufbau principle, and we want to be able to reproduce the Aufbau diagram, and we want to be able to write a full electron configuration for any atom or monatomic ion using that Aufbau diagram. So polyelectronic atoms, more than one poly electron. So everything other than hydrogen, essentially. Now, the problem, and we saw with Bohr's model, was he couldn't account for electron-electron interactions. Well, as electrons are added to an atom, we have a couple of different forces at play. We have the electron-electron repulsion between the electrons, and we also have the attraction of the nucleus for the electrons, and that's all going to change the energetics of the orbitals, okay? And this leads to what we call the Aufbau principle, or Aufbau actually means the building up principle. So, the Aufbau principle states that as electrons are being added to an atom, the energy of the sublevel is going to change, okay? Where in hydrogen, where we have only one electron, this would satisfy hydrogen, where we have just n equals 1, n equals 2, n equals 3, n equals 4. That's what we saw with the Bohr model. But when we start actually adding electrons, we see that we have extra sublevels, and those sublevels start to change their energetics. Okay? Now, the way that we follow the Aufbau diagram is actually pretty simple. We have n equals 1, that is that L equals 0, that is the 1s orbital. Then, if n equals 2, we have two possible values for L, that's 0 and 1, so that's the 2s and the 2p orbital. For n equals 3, we get the 3s, the 3p, and the 3d orbitals. For n equals 4, 4s, 4p, 4d, 4f, and so on and so forth. Now, technically, from this diagram, we could also put here 8p, 8d, 8f, 7d, and 7f, and then 6f here. And they would follow the same sort of pattern. Now, this pattern is actually pretty simple. See the green arrow here? We follow the green arrow down from tail to tip. We would fill up n equals 1, that 1s subshell. Once we filled that up with electrons, then we follow that little blue line there to the next tail, and we would fill up n equals 2, the 2s here. Then, if we have more electrons to add, we would move to the 2p. From the 2p, we would move to the 3s. From the 3s, we'd go to the 3p. But from the 3p, we actually get a mixing of our orbitals. The 4s orbital is actually slightly lower in energy than the 3d orbital. So you can see that there's a little bit of a splitting pattern here, where we've got the 4s and then the 3d. So we would fill up 4s, come back, start filling up 3d, then to 4p, then to 5s, and so on and so forth. So we can write electron configurations for substances, and the electron configuration is just going to show us a shorthand of where the electrons are at and what they're doing. A typical electron configuration would be shown as such. There's a number that starts off our electron configuration. This number, all of the numbers in front of a letter, are corresponding designations of n. So in this case, n is equal to 1. We use the subshell, the L value, but we use the letter, so this is S, so L equals 0, this is the 1s subshell, and we're going to put 2 electrons in there. We're going to use the 2 as a superscript. So if we have a slightly larger, longer electron configuration, I've got 2 electrons in the 1s, 2 in the 2s, and 5 in the 2p. How many total electrons is that? There's 2, 2, and 5. That's 9 electrons total. If this were an element, we would be dealing with fluorine. This is the electron configuration for the fluorine atom. We can also draw this in what we term a box diagram. Now, box diagrams are kind of nice because they show us that there are the number of orbitals that are existing within each of the subshells. So in our 1s subshell, we have one orbital, the s orbital. We can put 2 electrons in there. We represent electrons with arrows. They must be of opposite spin. So m sub s is actually dictated by an up arrow or a down arrow. That is how we can actually show the spin. So in this case, we've got 2 electrons in the 1s, 2 electrons in the 2s. That's how many electrons? That's 4 electrons. This means we are dealing with beryllium atoms. So let's practice electron configurations, and we're going to do the shorthand version in this section. So let's start off with chlorine. Chlorine has 17 electrons. Okay? Now, my Aufbau diagram, you notice I don't have a picture of it, but the thing is I can actually recreate the Aufbau diagram pretty simply. All I have to do is I just start with 1, 2, 3, 4, 5, 6, and 7 down the side. Okay? I'm going to stop at 7. I know the book goes to 8, but I'm just going to stop at 7. Then I'm going to write an S next to each of these. S, 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 S. All right? Then I'm going to go over 1 and down. And I'm going to write 2, 3, 4, 5, 6, 7. And next to these, I'm going to place the letter P for my P subshells. I'm going to go over and down 1, 3, 4, 5, 6, 7, and this is where my D's go. Over and down 1, 4, 5, 6, 7, and this is where my F's go. Now the key here is I'm going to draw lines at 45-degree angles through my numbers here. So, through the 1s. Well, after the 1s comes the 2s. That's the hardest one, is to remember that get the 2s in there. Then 45 degrees down, I'm going to get the 2p, which is then going to go through the 3s. Then the 3p through the 4s, the 3d through the 4p through the 5s, the 4d 5p 6s, 4f 5d 6p 7s, 5f 6d 7p, 6f 7d, and finally 7f. So there's my Aufbau diagram. It's actually pretty quick to recreate. Okay? So I've got 17 electrons that I need to put in here. So I'm going to start at the 1s subshell, and I can fit 2 electrons in there, so I'm going to put a 2 as a superscript. Following the tail, or the tip to the tail, now I'm going to fill up the 2s. So 2s can have 2 electrons total. Following my tail, my tip to the tail again, that gives me the 2p's. Now, the 2p's, remember each p orbital, or each p subshell can hold 3 orbitals. Each orbital can hold 2 electrons. So that's a total of 6 possible electrons that can be held in the p's. And since I've got 17 electrons, I've got to fill up p completely. So that's 2p6. After 2p6, then I come down to 3s. So I can put 2 in the 3s. Okay, now it's good to stop and check. What have I got? I've got 2, 4, 10, 12 electrons. That means I've got 5 more electrons to deal with. Alright, so after the 3s, I go to the 3p orbital. The 3p, I've only got 5 electrons, but the p's can hold 6, so I only need to put 5 in there. And there is our shorthand electron configuration for chlorine. All right, moving on to manganese. Now manganese is element number 25, which means it's got 25 electrons. Now, I don't have to reinvent the wheel here. I've already dealt with 17 of those electrons in chlorine. So, I can actually just start from where I stopped in chlorine, the 1s2, 2s2, 2p6, 3s2, 3p5, right? But I need to add more, so I'm going to add one more to that, so that's 3p6, because I can total up 6 total electrons in that section there. After 3p6, I come to the 4s's. So 4s, I can put 2 of those in there. After the 4s, I come to the 3d's. Now I can hold total of 10 electrons in the 3d's, but how many do I need? Well, currently I have 2, 4, 10, 12, 18, 20. I only need 5 electrons, so 3d5. That is the shorthand electron configuration for manganese. Moving on to the potassium ion. Potassium is element number 19, which means it usually has 19 electrons, but this is the potassium ion. It is a cation, which means it has lost an electron. So instead of having 19 electrons, this has only got 18 electrons. So we can see that if we use chlorine, which has 17 electrons, 1s2, 2s2, 2p6, 3s2, 3p, I can add one more to chlorine to get the potassium ion. So 18 total electrons. 1s2, 2s2, 2p6, 3s2, 3p6. And finally, the sulfur ion, the S2 minus. This has gained 2 electrons. Sulfur normally has 16 electrons, but it's gained 2. So now it has 18 electrons. Well, hey, the potassium ion had 18 electrons. The sulfur ion has 18 electrons. They've got the same electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6. If two things have the same electron configuration, we call this isoelectronic. Iso means the same, electronic, isoelectronic with each other. They have the same electron configuration. If we have a series of these guys, we can write what we call the isoelectronic series. You may notice, if you take a look at the periodic table, that the potassium ion, the sulfide ion, the chloride ion, and argon all have the same number of electrons, 18. They would all have the same electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6. This would be the isoelectronic series. In section 10, we're going to talk about the development of the periodic table, and you need to be able to state the common ions formed by family, which, let's face it, we should already know. The modern periodic table was developed by two men independently, Lothar Meyer and Dmitry Mendeleev, but Mendeleev gets most of the credit. It is arranged in order of increasing atomic number, even though that's not how it was arranged. That's what it ended up being, is an increase in atomic number. Now, when you increase atomic number, you're also going to increase electrons. And it turns out that there's actually a really neat relationship between the modern periodic table and the electronic structure of the atoms. We just talked about the isoelectronic series of sulfur ions, chloride ions, argon, and potassium. Well, why are they isoelectronic? Well, because they all have 18 electrons. What do we know about argon? Argon's a noble gas. It's got a very stable electron configuration. It doesn't bond with anything very easily, so it's a stable position. So the fact that sulfur forms a 2- ion, the fact that chloride forms a 1- ion, the fact that potassium forms a +1 ion, the fact that calcium forms a +2 ion, all stems from trying to reach the noble gas electron configuration. That's a stable electron configuration. So this is why all of our ions that we were told to memorize at the beginning of the course, group 1A forms +1, group 2A forms +2, group 7A forms -1, 6A -2, 5A -3. It's all because they're trying to be like the noble gases. In section 11, we're going to use the periodic table to fill orbitals. We'll demonstrate the relationship between the Aufbau diagram and the periodic table. We need to memorize the periodic table orbital blocks. We'll talk about Hund's rule, and we'll have to be able to do box diagrams for electrons, and write noble gas shorthand electron configurations, and talk about core and valence electrons for an atom or an ion. So there is, as I said, a relationship between the modern periodic table and the electronic structure. It turns out that we can break the periodic table into blocks based upon where the electrons are inhabiting. So we have these blue blocks. The blue blocks are what we call the S block. They are S block elements because that is where their outermost electron ends up, in an S subshell. Okay? On the other side of the periodic table, the rest of our main group elements, these green elements, this is our P block. Why are they P block? Because their outermost electrons are in the P subshells. Our transition elements are in the pink. This is the D block, because their outermost electrons are in the D. Actually, not their outermost electrons, but that's where they end up. And then finally, we have our inner transition metals, the lanthanides and the actinides. This is our F block. Now, the modern periodic table, if you memorize the blocks, will help you to fill electron orbital diagrams. How, you might ask? Well, let's take a look at, say, I don't know, let's do chlorine, because we did that before. We know that the electron configuration from chlorine, using the Aufbau principle, was 1s2, 2s2, 2p6, 3s2, 3p5. Right? 17 electrons, 10, 12, 15, or 10, 12, 17. Yep, 17 electrons. Now, if I take a look at the diagram here, my period number corresponds to my n level. So n equals 1, the only things that stop at n equals 1 are hydrogen and helium. So n equals 1, this would be the 1s1, 1s2, that's that portion there, the 1s2. Move to lithium, this is period 2 in the S block, so period 2, 2s1, 2s2, so that's the 2s2. We jump over to boron here. Now this is in the P block, and it's in period 2, so this is 2p1, p2, p3, p4, p5, p6, 2p6. After neon, we come down to sodium. This is now in period 3, the S block. So this is S1 and S2, the 3s2. Moving across, we have the P block again in period 3, so 3p1, 3p2, 3p3, 3p4, 3p5. 5. And we can do that for any of these elements. It just happens to work out perfectly that that is how the table is set up. We also have something else that happens. We have what we call Hund's rule. And there are several different ways to state Hund's rule, but the energy of the atom is lowest when all of the electrons are in the ground state. And energy is also minimized when spin is maximized. So that means that we half-fill orbitals before we pair electrons. This is best seen in a box diagram for something like oxygen. As we're adding electrons to our oxygen atom, we start off in the 1s's, so 1s spin up, 1s spin down, 2s spin up, 2s spin down. Now when we hit the 2p's, we could start doing spin up, spin down, spin up, spin down, but it turns out that energy is minimized if we half-fill these orbitals before we pair. So if I'm adding these electrons, I would add 2p to this guy, spin up to this guy, and spin up to this guy, before I'd come back and add my down arrows. So spin up, up, before down. So let's practice a box configuration for these guys. So instead of drawing boxes, however, chemists are lazy, and I tend to just draw lines instead of full-on boxes. So forgive me for being lazy, but here's my 1s, my 2s, my 2p's, remember there are 3 of them, my 3s, my 3p's, and so on. So I've got 17 electrons to fill. So I start by spin up, then I fill it up. Okay? Now I use half arrows because technically we use half arrows to represent electrons, but half arrows are kind of a difficult font to find, so sometimes books use whole arrows. 2s, spin up, then spin down. When I hit the 2p, then to follow Hund's rule, I'm going to half fill these guys before I come back and pair. Okay, so that gives me 2, 4, 10 electrons. 11, 12, 13, 14, 15, 16, 17. Now let's do this for manganese. I've got my 1s, my 2s, my 2p, my 3s, my 3p. Next comes the 4s, then the 3ds. There are 5 of those. So we had 25 electrons in this. So we start off, spin up, spin down. Then we hit the 2p's, and then it's spin up, spin up, spin up. Then down, down, down. The 3s, up, down. The 3p's, up, up, up. Then down, down, down. The 4s, up, down. Now that gives me 2, 4, 10, 12, 18, 20 electrons. That means I have 5 more electrons to place. The 5 electrons must then each be spin up to half fill that 3d orbital. So manganese, we would expect to have 5 unpaired electrons, and in fact it does. Now since potassium and sulfur here were not nearly as impressive because it's very similar to the chlorine, I'm actually going to replace these with chromium and copper. Okay? Chromium has 24 electrons. So we would expect it to look, well, we would expect the electron configuration for this to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Okay? Now, a box diagram for this would be 1s, 2s, 2p, 3s, the 3p's, which I didn't draw very well, 3p, 4s, and then our 3d's. We would expect it to look much like manganese. Up, down, up, down, up, 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 down, 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 up, down, up, up, then down, 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 up, 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 and then up. 24 electrons. Now, this is another aspect of Hund's rule. Energy is minimized if we have half-full orbitals. So what ends up happening is this electron here ends up being promoted to the 3d. So instead of having this electron here, we end up moving it there. So what we end up is 5 unpaired electrons in the d and 1 in the 4s. The electron configuration really is then going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. It is much more energetically favorable for each of these to be half filled. Now, you're wondering about that promotion of the electron. Remember, the 4s and the 3d electrons are very close in energy. So it doesn't take much for that electron to be bumped up a little bit, and the amount of energy you get back from having this maximized spin actually more than accounts for the energy required to make the bump. Now, copper is a similar situation, but with copper, what we have is 29 electrons. We would expect this to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. But what we get instead is a promotion of one of those s electrons to the d's to give us 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. That d orbital was so close to being filled up that it would rather have a full d orbital because that closes out n equals 3. It closes that whole subshell than to have a pair of electrons in the 4s, which is slightly lower in energy. So it's better to close the shell than it is to keep the shell open and have an extra pair. So these are the exceptions, and these are familial exceptions. So things in the chromium family and things in the copper family tend to do this. Now you might be curious as to why all of this writing. That's a lot of writing, and if chemists are lazy, then why do they write so much? Well, truth is we don't. We don't write so much. We actually have a shorthand, okay? And this shorthand has to do with the noble gas configuration. We talked about how the noble gas is a very stable electron configuration. So let's illustrate this concept with lithium. So the shorthand is I look to the element that I have, and I look to the noble gas prior to that element. The noble gas prior to lithium is helium. So what I do is I write helium in brackets. This means that I have all of the electrons that are associated with having helium, the 1s2, okay? And then I start my count over to finish up my electron configuration. In this case, this is 2 in the s group, 2s1. Now, that is not shorter than 1s2, 2s1, but they are equivalent. They are the same things. So using the noble gas configuration like that, the noble gas shorthand, doesn't save you much there. But let's do something like chlorine. The noble gas prior to chlorine is neon. So what I would do is I would write the core of neon, then start my count. I come down here, so this is 3s1, 3s2. Then 3p1, p2, p3, p4, p5. 3p5. That's a little bit faster than 1s2, 2s2, 2p6, 3s2, 3p5. It really becomes important when we do something like, oh, I don't know, iodine. Okay, iodine, something way down on the periodic table, 53 electrons. That is a lot of electrons. So, the noble gas prior to iodine is krypton. Okay, so we'll start with krypton, and I will write Kr, and then from krypton I go to rubidium, so that's 5s2, from the 5s. Now here's where it gets to be weird. Okay, you would think that this would be the 5d, but remember that with our d block, where do d orbitals show up? They actually show up in period 3, but they're just not filled. So when we start going through the d block, we didn't talk about this, but when we start doing the d block, this is actually n minus 1. So this is 4. This starts the 3 d's. So this is the 3 d's. This would be the 4 d's, the 5 d's, and the 6 d's. In other words, for the d's, it's period number minus 1. For the f's, when we do the f block, this is actually period number minus 2. So what we see here is this is the 5 f's and the 6 f's. Okay? Alright, so we did the 5s2. This goes then to 4d, 1, 42, 43, 44, 45, 4d6, 4d7, 4d8, 4d9, 4d10. So we have the 4d10, and then 5p1, 5p2, 5p3, 5p4, 5p5. That is much faster than writing it out longhand. So we have a couple of different spots that the electrons can occupy. We can have electrons in the core or the valence. Okay? The electrons in the outermost energy level are what the world sees. These are farthest from the nucleus. These are the highest in the energy. These are what we call valence electrons. These are the electrons with the greatest n value. So to determine the number of valence electrons, you count up all the electrons in the electron configuration that have the same n value, that is the largest n value. Any other electrons, the electrons in the inner levels, are called core electrons. Core electrons are not seen by the world, they are hidden. Okay? So let's do a quick example here. If I have an electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8, how many valence electrons do I have? Well, I look for my biggest number of n. So 1, no, 2, no, 3, no, 4, 3. 4! Hey, look at that. I have 2 valence electrons. How many core would I have? Well, 2, 4, 10, 12, 18, 36 core electrons. 36 core electrons. Now, for our main group elements, this is actually really easy. The number of valence electrons equals the family number. So, for group 1, there's 1 valence electron. For group 2, there's 2 valence electrons. For group 3A, 3, 4A, 5A, 6A, 7A, 8A, it's just the family number to tell you the total number of valence electrons. We will see in later chapters that valence electrons are really important because that is what the world sees. This is what is going to be used in bonding.